Hello, everybody. Good afternoon. So you all are ready to hear the lecture. So far in this series of lectures, particularly among the various processes employed in research methodology, so far we have done. First, we did formulating and clarifying research topic. Then we did literature survey, and last time we did research design and also collection of data. So now it is the time to look into data analysis. And after this, maybe a couple of lecture we will do data analysis, and then we will go writing of. Most research studies result in a large volume of data. But as we discussed today, statistics makes it possible to summarize the meaning of huge number of measurements in a compact form and explain the significance of measurements when chance makes them uncertain. So these are the things we'll in detail address today. Any attempt to measure in an experiment, suppose you measure values, you will invariably find they vary from one trial to next. Thereby introducing uncertainty in the true value. No measurement you can make uncertainty free, and this type of uncertainty is called also random error or statistical error. So we will see all those things. Statistics provides a means to quantify precision of set of measurement. That is one thing statistics does. Even if you have a distribution of measurement for a same quantity, but then using statistics, you can quantify the precision of the value. Statistical analysis also help us to reduce many numbers, I told you also earlier, to a few, and help us to generalize the result. Suppose, let's for example, I want to let's say I want to measure length of all the fishes in a pond. Suppose this length of all the fishes, let's say I put in centimeter. Suppose let's say 10 centimeter, 20 centimeter, 30, 40, 60, like this I did. So then I make a histogram, the number I got. Suppose I made a measurement and I got numbers like this. So I got certain number with a 10 centimeter length, certain number of fishes 20, certain number of fishes 30, and similarly 40, 50, and 60. Whether this giving all these numbers makes sense, or if I want to just find the average of all these numbers. So if I find the length of average length of fishes, what I will do, I will just add up all the all the fishes and xi divided by total number of pieces. So this will give me what is called the average length. And suppose I want to characterize this distribution little, more precise way, then I can define one more parameter, which you tell me that okay, its average is a certain value, average is x average, and I want to know how much it has scattered around the average. So then also I can write what is called variance of the sample. So that I will write yeah. So variance is defined by this, where you x average you take from the this past expression and put it here, and xi is the each event, and the sum over that, and you get this. क्या हो गया इसको हटा? So what I want to tell you is whether when I give a average and a standard deviation, these two numbers, that makes better sense to us, or if I give a all this plot and all the numbers of a distribution of the length of a fish, maybe these two numbers will be giving better visualization to us, rather than giving whole. If I give a whole table where length of all the pieces will be written. So this is one of the example where many numbers has been reduced to few, to be precise, only two numbers, and they can convey even better than getting information about the individual detail. So two of the main reasons to learn statistics are to deal with the measurement error. When you measure one, as I told you, in experiment, any variable, you get a number. Again, when you measure, you are getting a different value. So that gives a distribution of values. So that gives a that much uncertainty. That is what we call random error. And these statistics will help us to deal with measurement error, and to able to describe distributed quantities like I saw in this plot, to express them in less number of variables, and also convey better. So this is all about to that is what we are using statistics to take advantage of these things, in particular in a experimental physics. So the next thing we'll see now is as I told you, statistics also is useful when you have a distributed quantity. The quantity is distributed, then how statistics can help us. So we'll see that. So something called probability distribution. You may be knowing all these things, but we'll start from the scratch. Probability distribution are one of the central idea underlying statistics. It is very important in statistics, the probability distribution, where the measurement produce a range of values. So any measurement which produce a range of values, probability is defined as the chance of occurrence of an event. Suppose you have a measurement where you have a possibility of producing a large number of values. So then the probability will define that occurrence of particular event. What is the probability? That is will be defined as the probability. and many real life subjects to probability. Many in real life events, they're subject to probability. Like I can write. Suppose you want to find probability of getting just a simple example, getting head while tossing a coin. While tossing a, they call it pair coin. This will also, follow certain probability distribution for all the possibility. We will see that. Similarly, you can say, suppose, you know, in your daily life, you observe this type of, probability, like, probability of rainfall. Suppose rainfall on a particular day. To understand the concept of probability, one should be clear with a certain terminology. So one is called the experiment. So what is the experiment? You have to define. Suppose in the present case, let's say I will take the first one. Tossing the coin. That is our experiment. Okay. Acha, okay. What a minute. Just hold on. बड़ा हो गया. अच्छा, sorry. Sorry. Yeah, we're talking about some of the terminologies to understand the probability. One is the experiment. Then you have to know what is sample. What is called sample space. Basically, sample space is a list of all outcomes. Suppose now we are studying, suppose head or tail. It is basically sample space is a list of all outcomes. And then event. Event is actual outcomes. So these are the three things you have to know so that you can define what is the probability. Let us take, we have taken two coins and you toss it 4 times. Then you would see what do you mean by probability through this example. Let's see first the first coin, and we have second coin. Your right outcome. So suppose first coin get head, second coin also head, so outcome is head and head. Similarly, you can get head and tail, outcome is head and tail. Or you can get tail and head, and outcome is tell and head. And also tell and tell and tell and tell. So these are the outcome if you have two coins toss, I know, 4 times. So what is the sample space here? Sample space is all the list of outcomes like HS, HT, TH, and TT. So there are spaces. These are the 4 spaces. And what is the event? Event is H, TH. Suppose you don't differentiate between TH or HT, then you have this, and TT. So then I can write the frequency 1, 2, 1. So probability, how do you define? Probability is equal to number of outcomes favorable to the event. Somebody, whatever you want, 2 head or 2 tail or 1 head, 1 tail, then divided by total number of outcome. So in this present case, you could write the probabilities. Let's write here. P of H T, that will be 2 by 4, that is equal to 0.5. I write probability of H and H, that will be 1 by 4, that is equal to 0.25. And if I write T and T, that is again 1 by 4, that is equal to 0.25. And interesting that you have to make sure that your total probability is always 1. 1, all your event. You want to your number of events. P, suppose you write xj is equal to 1. You see here 0.25, 0.25, and 0.5. If you add all 3, that is coming out to be 1. Okay. There are many distributions we come across. Like, suppose I write a distribution, something like that. If I put this axis is probability, and this is some variable. Suppose it is coming constant. This is a constant probability. And among all these probability, we'll see one by one. One of them is very important, and it is called the binomial distribution. There are quite a few distributions. So one is called binomial distribution. This distribution is based on what is called this distribution is a condition. When it is satisfied for condition, then whatever distribution it gives, that is called binomial distribution. Those four conditions are called uh, for now the process. If any process satisfying these four conditions, like one, it consists of n trials, and two, each trial has binary outcome. Binary outcome. Three, probability of success is constant from trial to trial. Trial to trial. Fourth condition is trials are independent. If any process satisfying this four condition, then the distribution it gives, that is called binomial distribution. Suppose you want to find some, let us take the same tossing of coin. If you want to find m heads in a trial, suppose you want to find m heads in n trials, trials of the pair coin, then the probability of finding m heads is given by NCM p to the power m and q to the power n minus m. This will be the probability of observation. Suppose you want to also plot what is the probability of finding 0 heads, 1 heads, 2 heads, 3 heads out of n trials. So you can, the probability is given by this, where p is basically half and your q is equal to 1 minus p, that is also half. If this is the case, suppose you want to find n is equal to 3, then you will see P0, if you calculate using this expression, P0 will be 1 by 8. And P1 will be 3 by 8. And P2 will be again 3 by 8. And P3, the probability of 3 heads will be 1 by 8 again. So this distribution will be a something like, it is called the binomial distribution. And there is a, suppose you want to find out the mean of this mean, you can always find out m, then npm. So that will be your mu. So this will come out to be NP. You can calculate this. Similarly, you can find out also sigma. As I've given sigma, you will do the same thing. You will write a, same expression, but only you have to write here mean m minus mu, and then you do this is because your sigma will come. Sigma, it will be sigma square, and then sigma will be root of that. It will come as n. You can do this as exercise. This will come like this. This is what is it is a discrete probability. This is discrete probability, but you can if in the limit your dx going to 0 or going to very small value, become very small, then you can this probability can be written also like a over the whole space is equal to 1. So this is what I showed you is a discrete probability distribution. You can do this exercise and then plot and see how it is going for a number of trial increase and how it is changing. But the most important continuous, but this is what I showed is discrete, but when you go to continuous domain, the most important continuous probability distribution that is used in physical sciences is what is known as the normal distribution. Because most of the physical processes they follow this distribution. Also, this is called Gaussian distribution. Or sometimes called bell shape, because it looks like a bell that is in temples you hit the bell, that bell shape also it looks. So sometimes it is called bell curve. And if you know the two quantities like mean is mu, and width sigma, or standard deviation, then you can write the probability. It will be 1 by sigma square root e to the power minus x minus mu square by 2 sigma square. So this is the probability distribution for continuous distribution. This is mostly used in all physical sciences or biology, everywhere, all over this is used. Whenever it comes to continuous probability distribution, this is the normal distribution or Gaussian distribution or bell curve. And if you integrate it over the space, you integrate over minus infinity to plus infinity, and this will give you, this is 1. So now, you know that these are the distribution that we encounter in real life situations. But then, what one has to do, one has to link, basically the central concept of statistics is to make use mathematical results about probability distribution to estimate the likelihood of observing various results from a data. For this process to work, you will have to make a connection between the data you have obtained and some theoretical probability. Because when you do a experiment, suppose you measure certain values, x1, y1, sorry, x1, x2, x3 up to xn, and then you can see some average and also some standard deviation. If some other person also does the measurement on the same system, he may not get exactly same numbers, but his results will be statistically equivalent because they come from the same distribution. So, when you do an experiment, you rarely know what is the distribution. So, exact distribution we don't know, but sometimes what you do, you only make small measurements, and suppose you know that this distribution will be a Gaussian distribution, then you find their average and sigma, and then you say that okay, my experimental observation would be like this, and whatever you have found, you want to if you want to know what is the probability of observing other quantities, you can predict. So that's a beauty of statistics. So you know that this process is following particular statistics. If that is the case, then you don't have to really measure, all the sample space, but then you make a small measurement and find out what is the mean and what is the standard deviation. Then you put it into your probability expression, and then you can find out what are the possibility of obtaining, any number. What is the probability? So that's beauty of probability distribution. Suppose for a continuous distribution, you can write your mean as a mean. Normally, you write equal to, for a normal distribution, x px dx, and similarly you write sigma square variance dx dx. So this way you can find out mean sigma square. Then you can generate a distribution. Then you also can predict the possibility of obtaining, what is the probability of obtaining other values. One very interesting things in statistical physics is what happens if average number are increased. Suppose you have measured your average value mu, and also standard deviation also. Suppose you increase the number of observations. So what will happen to these values? Yeah, it's a very powerful result that tells what happens to sample mean as you take more and more data. If I go on taking more and more data, what will happen to my average value? And whether it will be different or what, we will see that. And you will see that it shows random errors can be reduced. Your standard deviation can be reduced. If you take more and more measurement, your standard deviation can reduce. This is a very powerful mathematical result in statistical physics. We will see this in a little detail to really understand how it is happening. And because this is you can always, because your random errors can be reduced by taking more and more data. So In principle, you can take a measurement to a well-defined accuracy by increasing your uh, number of number of data taking. Suppose you want somewhere my precision should be 1%. You can find out if I want to get a 1% error on my measurement, how much data I should collect. So that's a very important thing. I will see now how it depends our mean value with the number of data points. So this is a very famous problem in statistics. What is called a let me write a drunken sailor. Basically, what happens? A drunken sailor, he wants to go home, but he does not remember which way he is going. So each step he takes is in a completely random direction. Because he can go sometimes left, sometimes right. So he exactly doesn't know which direction he is going. So his motion is totally random. If that is the case, let us say when he moves to left, he goes by -1, some unit of distance. Or if he goes to right, he moves +1. So the sample space for this experiment is x -1 and +1. So when he starts from a particular position, let's say that is a position 0, he can go to left or he can go to right. That probability is okay. Probability of -1 is half, and probability of +1 going to +1 is also half. Suppose I want to calculate what is the mean distance it will travel after one step. So the mean will be defined as x belongs to, it has got 2 -1 or +1 x px. So this is equal to, if it is going to x is -1, then I write -1 into half. Probability going -1 is half. Plus is moving to +1, and the probability of +1 p is also half. So my mean is 0. So that means probability, if you want to calculate after first step, that is 0. But people can calculate the variance. Sigma square, that is sum over x, then x minus 0 square dx. Okay. So this you can write, or this is x square. So x is x can be minus a half, or it can be x is -1 or +1. So but this is being a square, so it will be always 1. So you will have 1 into half plus other one is also, because if x is minus or plus, it is being squared, so it is always positive. So 1 into half. So that is 1. No, that is correct. Suppose, the seller is starting from 0, either he can go to +1 or he can go to -1. So in an average, he is moving from his position is 1. So if sigma square is 1, so sigma is also 1. That's interesting. So now we will consider if he takes 2 steps, how things change. How sigma and your mean value changes when he takes 2 steps. Sorry. Second step. So if I write mu, this can be written as mean value. This can be written like this. x1, this belongs to space -1 and 1. And another one, x2 also belongs to +1. Then 2 steps, x1 plus x2 into it is px1 px2. So this you can write like this, x1 px1 here summation x1 and p x2 plus similarly you can write summation x1 px1 summation x2 px2. Okay. So this is basically mean position of x1 x2. Earlier we saw in the first step this is 0. So that makes 0 into this is probability sum over p2x1 plus 1 into 0, that is 0. So when he is taking second step, its mean is not changing. But what about variance? That is of interest. Now you define how the variance is changing. Sigma square is equal to x1, x2, x1 plus x2. Because mean is 0, so you can just square it. Px1, px2. So this you can write you could do this just to you bring x1, earlier it was 1, x2 also 1, and it will do, and this term will go to 0. It will go to 0. So what you will get is result 1 into 1 plus 1 into 1 plus 0. That is 2. If sigma square is 2, then you get your sigma root 2. So after two steps, the seller on average, after one step, he had moved 1 unit. We saw that sigma was 1. But after two steps, you see sigma is, but it is root 2. So that's interesting. So this gives the standard deviation or the uncertainty in measurement of x1 and x2. So this can be written as uncertainty in measurement of x1 plus x2 equal to root 2. Suppose, this root 2 is how it is coming. It is something like that. 1 plus 1, because each one had a uncertainty 1. So, you can see, suppose you have two quantities. So, variation in two quantities, if you want to calculate x1 plus y1. So, that can be written as a delta x square plus delta y square. This will see also. Now, from this also you can see. This also gives us confidence to write. Suppose you want to calculate errors in your average. So you do many multiple samples and then take an average. So when you get average, suppose you have three quantities you want to make average. You write x1 plus x2 plus x3 divided by 3. Because if you want to calculate just error in 3, so you can do that error in x1 plus x2 and plus error in x3. So that can be also written root 2 sigma square plus sigma square root, that is equal to 3 root 3 sigma. You can do this. So this can be generalized because if you want to take average of 3 number, so then your error is coming like this. If you take average, error on the average with this one. If you take, then it will be delta x1 plus x2 plus x3 divided by 3 is equal to root 3 sigma by 3. That is equal to sigma by root 3. This can be generalized to suppose a large number of measurements. So you increase your number of measurement, so error x1 plus x2 plus xn by n, that is your average mean. That can be given as error in your mean, so that is delta on your mean sigma by n. This is a amazing, general result. So your this we derived for a discrete values of n, but it is true for probability distribution, even for continuous distribution. And suppose you that error in x average, you can delta x average is basically, it will assume that that is the uncertainty in mean value. So it can be written as, and you write that as a delta x. This can be written as, and suppose your sigma is the average, your standard deviation of the sample. But suppose your standard deviation of the population, this is called. Even if you don't know, you can take for one of the sample and you can write there your sample standard deviation and number of events. This shows if you increase your number of event, the error on your measurement will go on reducing. So this is a very uh, powerful result. That is what we say that when you take more and more data, then your statistical uncertainty will reduce. And here we derived it for discrete distribution, but exactly the same argument holds for continuous distribution, because it is easy to formalize and visualize this discrete probability. So today we concluded that you see that how by just increasing the number of measurement, you can reduce the error in your measurement. That's the one thing we learned. So all the studies outcome, we can say that the true or the absolute value of a quantity cannot be established experimentally. Experimentally, you cannot find a exactly true value. So that the observed value must be compared with the most probable value, or mean. Mean value we have to take, and you have to, suppose you want to compare that with some theoretical prediction, then you have to take the mean value, because exact value we cannot determine experimentally. And also your statistics, it provides a means of quantifying the precision of a set of measurements. Suppose you have done a set of measurement, that what is the precision of that measurement that we can get by statistics. So next I wanted to do error analysis, but okay, we can, because it is already time. So we'll stop here. Maybe again next time we'll continue. Okay, thank you. Now you can ask any question if you want. The question, and if anybody want to ask any question, you can ask. Yeah. So this is a good question. In variance, if your number of n is very large, you can always take n. But n minus 1 is taken because suppose you have only one data point. At that time, for a single measurement, your variance is not defined. So you can't define a variance for a single measurement. So to take care of that, you have taken that n minus one. Other than that, that's nothing much on that, because only to take care of that, it is sometimes taken as n minus one. If n is large, then it doesn't matter. You can take n. Any experiment how to decide the maximum number of measurements considering limitation time? Yeah, when you are doing an experiment, what you have to okay, the time is one factor. Then you have to compromise somewhere, and you can find out that what percentage of error you can tolerate. That okay, you can do some problem related to that to find out uh, how much measurements should be done to to be within certain you know uh, uncertainty, because you want to say that I should be within 5% uncertainty, my results should come. If that is your criteria, then you can decide how long we have to take data, or how much data we should take. Poisson distribution, we can do that, but maybe will not. If you want, I can do that. That's no problem. But for us, we will these two, binomial and Gaussian should do, because most of the things they fall within these two criteria. How instrument accuracy? Okay, we'll talk about that maybe next time, because I was not having time this time. Next time we'll discuss on this. What are the different possible errors that could be there in real experiment? Okay, that also. Okay, we'll discuss this point maybe while doing error analysis. I wanted to do it today, but because we are running out of time, so next time we'll do this. How many data sets should we consider for the experiment? This you can again, it all depends. Okay, we'll do some problem. Maybe then it will be easier to understand that. Yeah, how much data we should take. Okay, we'll prepare some real problem that will give a better feeling. Okay. I think why is it okay? Sir, can you use real problem using Excel? You want to use Excel sheet? No, yeah, I think it is possible, but I don't know Excel much. You can do that if you want to do on yourself. You can do that. Okay, next time we will do how to really do the error analysis and things, and a few problem. So we'll do that. That will give a better understanding. But today I did most of the background, things. Real problem we have not taken up. So I thought to get an understanding, some basics we have to do. Most of things what has been done today are the basics. Okay, thank you. We'll meet again on Wednesday.